Welcome to lecture 23. Last time we have identified or characterized what are all the prime elements in the ring of Gaussian integers, and today we will see as an application which integers can be written as sum of two squares. So, last time we have identified which primes can be written as sum of two squares, and we have seen that if a prime is congruent to 1 modulo 4, then it can be written as sum of two squares. Today we will actually identify what are all the integers which can be written as sum of two squares. So, let us start. So, the question that we would like to address today is the following question, that which integers say n in Z, of course we are talking about positive integers, can be written as sum of two squares. That means what we would like to know is that let n be an integer in Z, then we want to write n as sum of two squares, that means a square plus b square, where these a and b are integers. So, we would like to see which integers, of course not all integers can be written as the sum of two squares. So, we would like to identify which integers can be written in the form a square plus b square, where a and b are integers. So, which is equivalent saying that now you can look this n, we would like to write it as a square plus b square. So, this a square plus b square is nothing but we can think of it as the norm of the element a plus iota b. So, that means which integers can be written as norm of an element in the ring of Gaussian integers, that is the question we would like to address here. So, which is equivalent saying that which integer n can be written as norm of an element of the form a plus ib for some. So, this norm I would like to denote by capital N. So, norm of a plus ib, where a plus ib is an element in the ring of Gaussian integer. So, this is basically equivalent to identifying all the elements in the ring of Gaussian integers of the form a plus ib, such that this integer n can be written as a norm of a plus ib. So, we would like to find out what are all a plus ib such that n should be equal to this norm of a plus ib. That is what we would like to find out. So, now let us, for this thing we need to understand what are the prime because any integer n can be written as product of primes, and then you can identify that whether the prime is congruent to 1 mod 4 or 3 mod 4, and accordingly you can write down decide whether it is an irreducible element or it is not an irreducible element in Zi. So, let us try to see what we can do. So, that is, write down the prime factorization of this integer n in Z. So, we are trying to write down n as product of primes. So, P1, P2, say Pr. So, this is a factorization in Z. All these Pi's are prime elements in Z, where these Pi's are in Z which are prime elements, which are prime integers. So, first we have written down all the the factorization of this integer n into product of prime integers. Now, you look that if this prime pi is congruent to 3 mod 4, then what do we know? Then this pi is in fact an prime element in Zi as well, that we have already learnt in the previous lecture. So, then this pi is an irreducible element in Zi, and what do we know about its norm? We know that its norm will be nothing but pi square. So, if pi is congruent to 3 mod 4, in that case its norm is nothing but this pi square. Moreover, we know that if your prime is congruent to 1 mod 4, in that case pi can be written as some pi I into pi I bar, where this pi I is an irreducible element in Zi, where this pi I is an irreducible element in Zi, with we have another thing, that this norm of this pi I will be nothing but pi. So, norm of pi I is pi. So, we have seen that these whenever we are writing this integer as product of primes p1 up to pr, then there are two choices for these pi's. Either it will be congruent to 3 mod 4, in that case these are irreducible elements in Zi, or these are congruent to 1 mod 4, and in that case it can be factorized further as pi I into pi I bar, where pi I is an irreducible element such that the norm of pi I is equal to pi. Now, we will be using this fact in order to give the in order to write this integer n as norm of some element a plus ib. So, now our aim is to find out or how to construct this element a plus ib from these pi's, so that the norm of this element will be equal to. So, our aim is to find out this a plus ib such that norm of a plus ib will be equal to this integer n. So, for that I will divide it into two cases. So, first case 1, so let n can be written as p1 p2 into pr, such that I am assuming for the first case that all these pi's are congruent to 1 mod 4, congruent to 1 mod 4. So, in that case what do we know? If pi is congruent to 1 mod 4, that means each of these prime can be written as sum of two squares or norm of some element. So, all these pi's are congruent to 1 mod 4, that is each pi is of the form pi I into pi I bar for some irreducible element pi I in Zi. So, then our question is, what will be the element a plus ib, so that norm of a plus ib will be equal to small n. So, what will be a plus ib such that norm of a plus ib is equal to n. That is what we are trying to identify, basically these a plus ib from this factorization. So, you can now be able to see, because you can see that if I consider my a plus ib as say pi 1 into pi 2 into pi r, in that case you can notice that what is the norm of this element pi 1, pi 2, pi r, this is nothing but, so norm of pi 1 into norm of pi 2 into norm of pi r, and norm of pi i's are nothing but pi's. So, this is equal to p1, p2, pr, which is equal to n. So, your a plus ib is nothing but if I take this factorization of pi is one of this factor from the factorization of pi's and take the product, that will be the candidate for a plus ib such that its norm will give you this integer n. So, if all these pi's are congruent to 1 mod 4, in that case definitely I will be able to write down this integer as sum of two squares, and the candidate a plus ib can be found in the following way. And you can see that instead of this pi 1, I could have chosen pi 1 bar also, that would not have affected. So, there will be not unique element a plus ib, there will be several choices for a plus ib. I can choose each of these pi I as pi I or pi I bar and take all the combination, all those gives you the element a plus ib such that its norm will be this integer n. So, let me just help you out with an example. So, let us consider the following example. So, question is, can this integer 17 into 29, can this integer be written as sum of two squares, as sum of two. So, 17 into 29, you would like to see whether this integer can be written as sum of two squares. So, you can first note that already the 17 and 29 are primes, and these are, both of them are congruent to 1 mod 4. So, note that 17 is congruent to 1 mod 4 and 29 is also congruent to 1 mod 4. That means these are not irreducible elements in Zi. So, I can factor. So, 17 I can write it down as 4 plus I into 4 minus I. So, this is the factorization of 17, and this 29 can also be written as 5 plus 2I into 5 minus 2I. And I would like to find out now this a plus ib. So, then a plus ib can be one of the factor from this factorization of 17 and one of the factor from this factorization of 29, and all the combinations will give me a plus ib. So, then a plus ib can be the following elements. As I have already told that a plus ib may not be unique, there might be several choices. So, here I will explicitly write down what are the choices for a plus ib. So, I can have either 4 plus iota into 5 plus 2I, which is nothing but 18 plus I, 13I, and next I can have 4 plus iota. Now, instead of 5 plus 2I, I can choose 5 minus 2I from here. So, 5 minus 2I, which gives me nothing but 22 minus 3I. Next, I can choose 4 minus I into 5 plus 2I, which is equal to 22 plus 3I, and then I can have 4 minus I into 5 minus 2I, which gives me 18 minus 39. So, you can check for all these elements, the norm is nothing but this integer 17 into 29. Not only that, you can observe that if I multiply all these elements by a unit element, then its norm does not change. Therefore, there are 4 units. So, each of them have again 4 choices. So, there are 4 units in Zi, and norm of a plus iota b into u is same as norm of a plus ib for an unit u in Zi. So, that means each of the element have 4 choices. So, there are total 16 possibilities. So, there are total 16 possibilities for each of this a plus ib, for a plus IB such that norm of A plus IB is nothing but this integer 17 into 29. So, I have all these 4 choices and then each of these 4 choices again have 4 choices because there are 4 units elements. So, that is why we are having total 16 choices. So, this is the case where I have considered all the primes are congruent to 1 mod 4. Now, we will see what happens if some of the primes are congruent to 3 mod 4. In that case, in which situation we can write the integer as sum of 2 squares. So, let us see. So, suppose case 2, here I am writing down say n as p1 square into p2 into pr such that my p1 is congruent to 3 mod 4 and the rest of these pi's are congruent to 1 mod 4. So, basically I am assuming one of the pi's is congruent to 3 mod 4 and rest of the remaining are congruent to 1 mod 4. So, for I equal to 1 to r. So, in this case what will be my A plus IB? So, you can see that if I this P1 is congruent to 3 mod 4, that means its irreducible elements and its norm is nothing but P1 square. So, in that case what will be the choice? So, then if I choose A plus IB to be equal to P1 into pi 2 into pi r. So, where you can see that each of these pi is pi I into pi I bar because these are not irreducible. I can factorize it further where these pi i's are in zi and irreducible with norm of pi I is equal to pi. Then you can see that norm of p1 into pi 2 into pi r is nothing but this integer n. So, in this case what I have to choose my A plus IB? I have to choose the factors, irreducible factors of this PI's which are congruent to 1 mod 4 and this P1. So, that means I need to have this P1 to be present in even power, because if it is not present in even power then its norm will, I cannot take that P1 as in the factor of A plus IB because its norm will always be P1 square. So, that gives me an indication that if I am writing down the integer as a factor, prime factors, then all those primes which are congruent to 3 mod 4 has to be present in even power, so that we can take that even power divided by 2, so that when I take the norm it will give me this integer n. So, if I summarize these things then I will get the following result. So, let me summarize and write down the main result now. So, let n be a positive integer and I am writing down the factorization of n. So, write down n as 2 to the power k into p1 to the power a1 up to pr to the power ar into q1 to the power b1 into qs to the power bs, where this p1, p2, pr are distinct primes such that each of these pi's is congruent to 1 mod 4. So, all these pi's I am assuming to be distinct and I am also assuming all of them are congruent to 1 mod 4 and these qy's are also distinct and this q1 up to qs are also distinct and these qy's are congruent to 3 mod 4. And not only that, I am also assuming that if this is the description of the factorization, then n can be written, as sum of two squares, that is, I should be able to write down n as a square plus b square, with a and b are integers, if and only if each. So, we have seen that if the primes which are congruent to 3 mod 4, they should be present in even powers. That means, all these bi's has to be even number. So, if and only if each bi is even, and if it can be written, then in that case the number of representations of n as sum of two squares is. So, how many possibilities are there? We will see that there are total 4 into a1 plus 1 into a2 plus 1 up to ar plus 1. So, this 4 you can see is coming for, because there are 4 units. So, whatever element I will choose, a plus ib, I can multiply that with this 4 units, and that will give me 4 possibilities. So, basically we are seeing that we up to units there are a1 plus 1 up to ar plus 1 are many possibilities. So, we have already discussed that when pi is congruent to 1 mod 4, in that case we can write, or if all these pi's are congruent to 1 mod 4, then we have seen it can be written as sum of two squares, and if these pi's are congruent to 3 mod 4, then it has to be present into even power. That all these things we have already discussed. So, now we will only prove that the number of representations will be this many. So, let us see how these numbers we are getting. So, the proof, we will prove that, assume that all the bi's are even, because bi's are even, then only I can write down n as sum of two squares, and these pi's which are congruent to 1 mod 4, those can be written as factored as pi 1 into pi 1 bar for I equal to 1 up to r. This is one thing. Then I can see that a plus ib can be written as, so you can see that I have 2 to the power k. So, 2 can be written as factor as 1 plus iota. So, one norm of 1 plus iota is nothing but 2. So, therefore, I can write down 1 plus iota to the power k, because norm of this is 2. So, this will contribute 2 to the power k, and then each of these pi's I will consider one of these pi I from there. So, I can write down this pi 1 into a1 1 pi 1 bar into a1 2, then pi r ar 1 and pi r bar a r 2. So, this is, and then these qi's are congruent to 3 mod 4. So, I have to consider the power to be b1 by 2 up to bs to the bs by 2, because when I take the norm of this, then norm of, so then you can see that the norm of this element will be nothing but q1 to the power b1. So, if I choose my a plus I b to be this element, then you can see its norm is nothing but the integer n. So, here I can say that I have some conditions, these a I11 and a12 will satisfy. So, with non-negative integers satisfying a I1 AI2 such that AI1 plus AI2 should be equal to AI for I equal to 1 to R. So, I have this representation where these AI1 and AI2 are non-negative integers which satisfies this equality. So, I can sometimes choose A11 to be equal to 0 and pi 1 bar to be equal to A1. So, all the combinations I can take where for each of them, and that will give me. So, how many choices I will have? I will have AI plus 1 many choices. So, since this AI1 can have values from, it can have values 0, 1 up to AI. So, total how many values each of these AI1 can have? Total AI plus 1 many values. So, that is why, so since each of these can have these many values, so there are total A1 plus 1 into AR plus 1 many choices. So, distinct elements A plus IB in Zi with norm n. So, I will be having total these many, and there are 4 units. So, I will multiply this with 4 and that will give you the correct count. So, since there are 4 units in Zi, the statement is proved. So, I am able to prove that we will actually have this many choices for A plus IB such that norm of A plus IB will be equal to n, and the condition which integers can be written in as sum of two squares. If I write down the factorization, then in that factorization the primes which are congruent to 3 mod 4 has to be present in even power. That is the condition I need to check whether an integer can be written as sum of two squares or not. And these pi's which are present, that there should be some pi's which and or otherwise 2 to the power k such that which should be congruent to 1 mod 4. So, this actually characterizes all the integers which can be positive integers which can be written as sum of 2 squares. So, this is one of the interesting question, and that we were able to answer using the concept of ring theory and applying it into the factorization technique that is we have applied in the ring of Gaussian integers. So, not only this, we can see those who are interested in number theory, they can actually see that in number theory this ring of Gaussian integers Zi plays an important role to answer many questions in number theory. So, today we will stop here. These are the applications that I wanted to give. These are the references for today's lecture. Thank you.